Everyone, welcome. Today we're going to be talking about measurement. So this is what we're covering today. It's coming from chapter 1 and then the start of chapter 2 in the textbook. We will cover units, significant figures, dimensional analysis, and introduce vectors, including position, displacement, velocity, and acceleration. Sounds like a lot, shouldn't be too long. In physics, we use International Standard or SI units. Time is measured in seconds, length in meters, mass in kilograms. The rest of these on this table, we're not going to use this quarter, but maybe you'll see them in the future. When we are working on physics problems, these are the units that we want to use, and all of our physics units should break down into seconds, meters, and/or kilograms. This also means that we'll have to convert units when they aren't in our typical physics units. For example, this value here is given in miles. And we don't use miles in physics, so we need to convert it. So we are going to, in this example, convert to kilometers, because sometimes we do use kilometers, but you might also convert it down to meters. So we multiply our value that we're converting by the conversion factor. So there's 1.609 kilometers in 1 mile. And we figure out the conversion factor first just from that like how many of this unit in this unit, or how many kilometers in a mile. And then we figure out this fraction just based on how we cancel out the units we don't want. So that's how we know that miles are on the bottom, because they will cancel out here. If they were on the top, they wouldn't cancel out. Anyway, so 60 miles times our conversion factor gives us 96.54 kilometers. And then we can round this to 97 kilometers. So let's talk about precision and significant figures. When the length of something is listed as 3 meters, it's reasonable to assume that the true length falls somewhere between 2 and 4 meters. If instead the length was given as 3.154 meters, we could assume that the true length or the true value falls between 3.153 and 3.155 meters. If we know that the length is 3.154 meters, but we list it as 3 meters, we're withholding useful information, and we don't want to do that. Let's talk a bit about significant figures. In determining how many significant figures are in a number, you start from the left and ignore the leading zeros. So here we have 3 meters. There's no leading zeros. There's literally just one number. That's easy, one significant figure. But then if we have 0.003 kilometers, you have to ignore these leading zeros. And then we just, again, have one significant figure. And also these are the same value because 1 meter or 1 kilometer is 1,000 meters. In this example, we have 3.0 meters. So that gives us 2 significant figures. There's no leading zeros, but then the following zero tells us that we are sure that it is more precise than just 3. And then this is what it would look like if we listed it in kilometers. Again, ignoring those leading zeros, 3, 0, 2 significant figures. So the other thing to know about significant figures is you should not include more significant figures than you input. So we have an example here of 3.5 times 1.5. Each of these have 2 significant figures. If you put this in your calculator, you would get 5.25, but that's 3 significant figures. We do not have that precision in what we input, so our output should be rounded to 5.3 so that we're not making up precision that we don't have. And this is also true for multiplication, or well, that was multiplication, but this is true when we have different numbers of significant figures in the two numbers. So we have 3.5 and 1.537. So this is 4 significant figures. This is still 2. We plug it into our calculator, we would come out with 5 significant figures, which is way more than either of these. But 3.5, 2 significant figures, is our least precise value that we input. So our final answer should also match that in significant figures. So we should just round to 5.4. And there's also the concept of least significant digit or first doubtful digit. So 5.3 implies that the value falls between 5.25 and 5.35. Or also 5.33 implies that the value falls between 5.325 and 5.335. When adding values, the final result should not be more precise than the least significant digit. So for example, if we add all 3 of these, 2.5 plus 3.01 plus 1.594, we get 7.104. But our least precise digit is this 0.5 here. So we need to round so that it matches with the 7. So 7.1 instead of 7.104. Another important concept is dimensional analysis. In this example, we'll talk about force, which we'll learn about, I think, next week, actually. So force has units of newtons, which are kilograms, meters per second squared. So kilograms, meters divided by second squared. Kilograms are mass, so I'll list those with a capital M right now. Meters is length, so capital L. And seconds is time, so capital T. So this is what the units of force look like. Mass times length times time to the -2, or divided by time squared. Either those are equivalent. Let's do a quick self-check here. Pause the video and answer the question. Velocity has units of meters per second. Which of these shows velocity? Is it A, L times T? Is it B, M times T? Is it C, L times T to the -1? Or is it D, M times T to the -1? Answer is C, L times T to the -1, or length divided by time. Okay, now we're going to move on to vectors. We're going to be using vectors a lot because a lot of quantities in physics have both a magnitude and a direction, which is described by a vector. The length of a vector shows the magnitude of the quantity, so how big it is. And the direction of the vector tells you the direction of the quantity. And so we have our example of our dog here, from the tail to the tip or the head. So this gives us the magnitude is this big, and it points to the right in direction. So this is how we are going to work to understand vectors. We have a vector A here at an angle phi from the positive x-axis. And we can break our vector into its x and y components using trig. So the x component is here, a cosine of theta, and we know it's cosine because the x component is going to be here along the x-axis, a sub x, and that is adjacent to the angle. Whereas y, we can put it along the y-axis. You can also, if it is easier for you to imagine it as a triangle, you can also imagine that the a sub y vector is here, and that puts it opposite to the angle phi, making it sine. If we know the x and y components, we can find the total vector here using Pythagorean theorem, the square root of the x component squared plus the y component squared. If instead we don't know the angle and we want the angle, but we know the x and y components, we can find that from tangent, because tangent is opposite over the adjacent. Opposite again is the y component, and adjacent is the x component. We can also represent this as a vector. And so it is the x component times I hat and the y component times j hat. Let's take a look at I hat and j hat really quick. So they are just unit vectors, meaning 1. So they don't alter the magnitude of the value. They just tell you if they're in the x or y direction, and eventually also the z direction, but not yet. So when we multiply the magnitude of the y component by j hat, it's just saying that that is the direction. And same with the x component. So when dealing with vectors, there are specific rules around addition. So here we have two vectors, b and a. And if we want to know what vector s is, and it's equal to vector a plus vector b, we do this. We'll move b from here to instead the tip of vector a. And then, so it goes tail to tip of a, tail to tip of b, and then vector s goes from the tail of a to the tip of b. There's also like some an example of steps here that can be useful. Again, so tail is the end, tip is the pointy end. So we'll draw A, and then we put B at the tip, the tail of B at the tip of A, and then we draw the vector from the tail of A to the tip of B. We can also do this numerically using the I hat, j hat representation of the vectors. So if A is given by these x and y components, and B is given by these x and y components, then S is just is also given by these x and y components, which are the x component of A plus B, the x component of B times I hat, and the y component of A plus the y component of B times j hat. So sometimes you just are given numbers, and it's just easier to do it this way. And here's the same method visually. So the A vector, we have our y component and x component. B vector, we have our y component and x component, and then we put them over in vector addition form. And you can see that the y component of S is just the y component of A plus the y component of B. And then the x component of x, because B is in the opposite direction of A, it ends up being A minus B. Speaking of minus, we can talk a little bit about subtraction too. So it works just like vector addition, but we take the negative of the subtracted vector. So let's say we have, again, A and B, but we want to know what A minus B is. We will start with A, and then we will draw B starting with the tail at the tip of A, but it's negative B, so it's gonna just face the opposite direction and point down. And then again, we do the same thing where we draw our vector D, which is A minus B, from the tail of A to the tip of B, of negative B. So a vector has a magnitude and a direction. A scalar just has a magnitude. So if you multiply a vector by a scalar, it only changes the magnitude, not the direction. So we have vector A here. If we multiply it by the scalar 1.4, it will get bigger. If we multiply it by negative 0.5, it will get smaller and change direction, just in the opposite direction. Okay, now we're gonna talk a little bit about motion, just to introduce you to these concepts. So first up is the position vector. So we just talked about vectors and unit vectors in 2 dimensions. To introduce these topics, we're going to expand to 3 dimensions for now, but we'll go back to 1 or 2 dimensions before we do too much in 3 dimensions. So we have our 3D coordinate axes, which is X, Y, and Z, represented by I hat, J hat, and K hat. And then just to show you X, Y, Z. So we have our regular X and Y plane, and then Z is just perpendicular to that. So we have a particle here, which has a position indicated by the dot. And we can see that there's a vector pointing from the origin of our coordinate system to the position of the particle. And that is given by R, and it is represented by this equation here, which is just the X position times I hat, the Y position times J hat, and the Z position times K hat. And that's written in unit vector form. And next is the idea of the displacement vector. So instead of 1 position, we have 2 positions on the path. So at time 1, we're here, and at time 2, we're here. And each position has a position vector, R1, which was kind of the one from the previous slide, and then R2 with the new position. And then the displacement vector is the difference between these 2 positions. So using vector subtraction, another way to look at it is just vector connecting the particle from position 1 and position 2. Now let's talk about velocity, specifically average velocity first, which is the displacement. So what we just looked at, the change in position, divided by the time interval, which is just like the change in position, but change in time instead. And time interval is a scalar. So the velocity vector points in the same direction as the displacement vector. So for average velocity, it is the displacement divided by the time interval, and time interval is given by the final time minus the initial time. If we want the instantaneous velocity of the particle at any given moment, we need to reduce the size of the time interval so that the displacement vector approaches the actual path. So before, our displacement vector was like along the path, but not exactly perfect. But if we reduce the size of our displacement vector, it follows the path more precisely. But as the time interval approaches 0, it also means that instead of change in position or displacement over change of time, we need the derivative of the position with respect to time. And this is what gives us instantaneous velocity, and we will refer to this as just regular velocity. Average velocity will still be referred to as average velocity. Just a reminder about the derivative of a vector. This is the position vector R, given by X, Y, and Z magnitudes and their unit vectors. And if we're taking the time derivative of this, we just distribute the time derivative. So we end up with dx dt times I hat, dy dt times j hat, and dz dt times k hat. So we can turn, these become the components of the velocity vector. So the x component is dx dt, the y component is dy dt, and the z component is dz dt. And earlier on with that self-check question, we talked about how the units of velocity are meters per second. So it's just a reminder. Acceleration now is the change in velocity with time. So average acceleration, just like average velocity, is the change in velocity over the change in time, where change in velocity is the final minus the initial. But this is average. For instantaneous acceleration, we have to, again, reduce the time interval and take the derivative of velocity with respect to time. So the instantaneous acceleration is the derivative of velocity with respect to time, and then each component is the derivative of that component of velocity with respect to time. And so what this ends up as for units is meters per second squared, because we're just dividing meters per second by another time. Okay. So that is everything for this lecture. So now you want to complete your post-lecture self-check, submit your discussion post and reply to someone else's, work on the application assignment, and then watch the last lecture for the week.